Hi, my name is Harrison Fisher. I'm a senior double major in physics and applied mathematics, and today I'm going to be discussing research which I conducted in assistance to Dr. Chad Rodekor on graphical analysis of the rope braiding process. We know that rope braiding has been around for a long time, but rope making has changed significantly throughout the centuries. Early humans created rope by twisting small strands together so that the larger strands could carry more weight. However, as technology progressed, we realized that braiding rather than twisting the strands created better results. So today, most ropes are braided by braiding machines, such as the one on the right side of your screen. In this diagram, you can see two main parts: a braiding mechanism on the left side and a capstan on the right side. So the braiding mechanism is what contains the individual strands of rope, and these strands are on their own carriers, which weave in and out of each other in order to create the braid in the middle of the diagram. Then the capstan on the right side is a turning wheel that takes up the completed braid. Both of these parts are driven by motors, which are controlled by a computer program, and you can run the motors at different speeds in order to change the characteristics of the rope which is produced. Here you can see a picture of a braiding mechanism. This is very similar to the mechanism at PC. Since I'm not on campus, I wasn't able to get the pictures that I would have liked to accompany this presentation of the machine that I worked on, but this is very similar. You can see each individual carrier, and you can see the strands of rope coming off of them. You can see the path in which they move in order to weave in and out of each other to create the braid in the middle of the picture. Now that you have some familiarity with the rope braiding process, I want to talk about some of the shortcomings which create the necessity for the research which I'm conducting. First of all, rope braiding is an extremely complex process. It's very hard to describe mathematically, which means that there's no model sufficient to fully show what the process does. Because of this, there's no predictive method for characteristics of rope, which means that there's no way to determine, based on the capstan speed and the speed of the braiding mechanism, exactly what characteristics of rope you're going to get. Some characteristics of rope include the amount of stretch in the rope, the thickness of the rope, and the tightness of the braid. As a result of there being no predictive method, manufacturers can waste time and resources when they don't get the right rope on the first try. That brings us to the purpose of the rope braiding research here at PC, which has several steps. First, to build a functioning rope braiding machine. We want to do this in order to be able to conduct experiments using varying speeds for the braiding mechanism and the capstan to produce different ropes. And once we produce those different ropes, we'll be able to observe and analyze the results in order to mathematically describe this process. Once we describe the process well, we'll be able to develop an accurate predictive method for rope production with specific characteristics. Right now, we're almost done with the braiding machine. It's in its final stages of development. I'm going to talk about some of the things which I did this year in order to get it closer to being done, and I'm going to list them on this slide and then talk about them in more detail on the slides following. So first, the base of the braiding mechanism was altered to correct its slight offset angle. Second, we raised the capstan several inches so that it would be level with the center of the braiding mechanism. Third, I'm designing a pulley system to connect the capstan motor to the capstan. And fourth, I created a three-dimensional plot of a static rope braiding system. So to align the braiding mechanism, we had to correct the offset angle in the base of the mechanism. What happened at PC was that when two of the metal parts on the base of the braiding mechanism were welded together, it created a slight offset angle so that the back of the machine was not perpendicular to the ground. You can see in the image that ideally you want that 90-degree angle between the ground and the braiding mechanism so that the tensions on all of the strands are the same. with the machine at PC, it was leaning slightly back or to the left as you look at the diagram, which caused the ropes near the top of the mechanism to have more tension than the ropes on the bottom. And this created a difference in the braid, which was not wanted. We want an even braid no matter where the strands are, so we need that right angle. So in order to create that, we had to make small extensions for the back legs of the base of the machine. After that, we had to align the machine in a different way. As you can see in the image, the top of the capstan should be level with the middle of the braiding mechanism. And in the machine at PC, it was a few inches too low. So Dr. Rodecor had me design and build a wooden base to put under the capstan in order to raise it to the correct height. I have some diagrams of this base here. You can see on the left side a perspective view, and on the right side a top-down view of the base, which I designed and built. It was made out of wood and metal rods, so I first cut the wood to the correct length and sanded it so that it was all the same height, and then drilled holes in the correct places in all of the long pieces of wood so that I could thread the two metal rods through the base in order to hold it together. Currently, I'm designing a pulley system in order to attach the capstan motor to the capstan. The reason we need a pulley system is because the motor shaft has to turn very quickly in order to create enough torque to turn the wheel. But in order to take up the rope, the large capstan wheel has to turn very slowly. We're looking at a factor of about 400 revolutions per minute of the motor shaft versus 2 RPMs for the capstan wheel. And you can see in this diagram on the left side that if directly attached to the capstan wheel, if the motor shaft turns at 400 revolutions per minute, then the capstan wheel will also turn at 400 RPMs, and that is impractical and won't work with the machine. So we need a pulley system in order to step down the speed. Here you can see a schematic of the system which I'm designing. You can see that the motor shaft is attached to a small pulley, which is connected with a belt to a large pulley. These pulleys are in a 3-to-1 ratio between large and small, which means that the angular speed of the large pulley will be 1/3 the angular speed of the small pulley. And so if the motor shaft starts at 400 RPMs, then it will be stepped down by a factor of 1/3, 6 times, which will create a speed in the capstan wheel of about 0.5 revolutions per minute, which would be the minimum speed since the motor shaft has to turn at least 400 RPMs. So that means that we can work with the capstan speed in order to have a working braiding machine with this pulley system. Here you can see alternate viewpoints of the pulley system. You can see on the top there's the front view with the motor shaft on the left and the capstan wheel on the right. And in the second picture you can see the back side with the capstan wheel on the left side. Although the capstan motor is not attached yet, the motor for the braiding mechanism is attached. So although we can't take up the completed rope as we make it, we can braid rope and create a static system. So we did that, and we set up a system with 16 strands, and we wanted to create a 3-dimensional image of that rope system using a computer in order to look at it more mathematically and analytically. So I'm going to take you step by step through that data collection process and then show you the resulting images. So first, we placed a level 2-dimensional grid underneath the rope braiding system in order to determine an origin and XY coordinates of each intersection point. This was done by looking at the intersection points of the strands, and when I say intersection point, I mean the point at which 2 ropes cross, and using a plumb bob to estimate the X and Y coordinates. And this was not perfect, as you'll see in a second. but we refined the system as we went, and we were intending on doing several tries at this, but the second half of the semester I wasn't able to be on campus, so that obviously didn't work out. Um, After we found x and y coordinates, we found a z coordinate of each intersection point using a height gauge and plotted each individual strand points in x, y, and z in the computer program Mathematica. After we plotted each individual strand, we overlaid each plot onto one coordinate system, each one with different colors to see the separate strands. And here you can see the resulting image. Here's the image which was produced using Mathematica. You can see each separate strand represented by different colors, and you can see how they all originate from the braiding mechanism on the left side, and they all come together near the region of intersection on the right. Here you have the side view of the same image, and here's the front view, and from this view you can really see the location of all the carriers on the machine, where the strands originate from. You can see how they kind of weave in and out of each other. Remember that this is only one point in time, and that all these strands will be moving during the process. Here's an up-close view of the region of intersection of the same image. You can see on the left side where the green and the orange strands cross, and below that where the red and the blue strands cross. And you can see those very clearly, but you can see that as it goes towards the right side, towards the region of intersection, that it becomes harder to distinguish which strand is which. And this is because the strands are becoming one braid as the machine braids the system. Here's a top-down view of the same image, and you can see, as I mentioned earlier, that this process was not perfect. You can see that by the point where the orange and the red strands meet on the bottom left of the image. And again, the intention was to do this more than once at different points and to refine the process and create more precise graphs to analyze mathematically. Here's one more perspective of the same image, this one from the front. And again, you can see that the data collecting method was not perfect. You can see the blue and the red strands at the bottom don't make sense with the rest of it. And that's because this was only our first attempt and we intended to do a lot more. So our collection method will only get better as time goes on. So now I'm going to talk about next steps of the research. First of all, we want to build the pulley system and connect the motor to the capstan. That's step one, so that we can get the braiding machine running and run tests. Second, we want to refine the data collection method, which I talked about a second ago, and create better plots. We want to create better images of the system so that we can run mathematical tests on them, and we want to create different images at different points in time in order to begin to see the changes and the motion of the system. After that, we want to start running tests, producing rope, and analyzing results. Once we get the machine running, we want to create different types of rope and see what factors lead to what types of rope, and that will assist us in developing a predictive method, which is our ultimate goal. We want to be able to predict the rope braiding process accurately so that we can save manufacturers time and money. That concludes my presentation. I'd like to thank the physics department, especially Dr. Rodekor, who worked very closely with me this whole year. He helped me at every step of the way, and I couldn't have done any of what I did without him. So I'd just like to thank him for all of his help. And secondly, I'd like to thank the people who put together this Honors Day Symposium. I know this wasn't the ideal way to do it, but without you, it wouldn't have happened at all, and I'm glad I got to be a part of it. So thank you.